Hello students, good morning. We are now studying or considering uncertainty relations in quantum mechanics. As we have already known in previous lectures that with a particle of energy E and momentum P, we can associate a field amplitude, and with the field of omega and k we can associate a particle of energy E and momentum P, both ways. But as we know that if we associate with a particle of E and momentum P a field of wave omega and k single valued, that means omega and k, that is monochromatic field, then this association with particle will not go for all time, but it will disperse after some time, because phase velocity and group velocity, they are different. The particle moves with group velocity, but the wave disperses after some time. So to keep it for the physically meaningful time, we constructed a pulse we constructed a pulse of superimposing by superimposing several fields or several waves of omega and k, where omega and k were superposed in a certain range, omega 0 plus minus delta omega, and similarly k varying in the range k0 plus minus delta k. And remember that omega is a function of k, so omega k, it is a slowly varying function. If we expand it using the Taylor series, then we can get this relation omega k equals to omega 0 plus k minus k0 d omega by dk, and evaluated at k is equal to 0 and the higher terms. But because, as we have seen already and we are remarking, that it is a slowly varying function of k, so the higher differential order terms can be neglected, and we are keeping only the first order differential, that is d omega by dk. Now what we are doing is that to keep the particle within a certain interval around x0. Suppose a particle is at x0, and then it should be confined within delta x plus minus delta x in such a way that this quantum quantum probability amplitude square should fall to the insignificant level at the boundaries of this interval, that is plus minus delta x around the x0 point. That was the idea. So we are constructing by superposition, and we have superposed several values of waves of several values in the range omega 0 plus minus delta omega, in such a way that omega by k will give us the phase velocity, which is c square divided by group velocity vg, and group velocity itself will be given by d omega by dk, and this is equivalent to the particle velocity or the group velocity or the pulse velocity vg, right? This is what we have seen. Now the question comes that if we superpose several waves, then what should be the amplitude of these constituent waves, and what should be its profile shape, or what should be its shape. So let us take that if we take the square wave pulse, then delta x and delta k using the Fourier analysis will give me delta x delta k product will always be greater than or equal to 1. This is what Fourier analysis says. Similarly, if we take that the profile of the waves that were superposed, if we take the amplitude of those ak, and if it is taken as a Gaussian profile, and if we take further constraint that if we take that the square of this square of the probability amplitude, that means probability density, falls to 1 upon E from the peak value, then we define such interval as you're writing delta term. Or if we say that it falls to half of the peak, then we signify that interval by sigma x, sigma k, sigma omega, sigma I sort of things, right? So this is what this equation 3 says. This is a minor thing. So this is how we define our uncertainty. Now you see that using the Fourier analysis, if we stick to the definition of our interval and such that at the boundary of the interval, the the value of the probability density falls to half. So the width sigma x, sigma k, sigma omega, sigma t is defined as half value width, right? So half width, and therefore the total width is plus minus, as you know, sigma of that particular variable x, k, omega or t, whatever, right? Then we say that the product of sigma x and sigma p, right? The product of the product of the product of sigma x and sigma p is given by this product is always greater than or equal to half sigma x, sigma k. Similarly, sigma x and sigma t star is always greater than half. I'm putting this as a sigma t star because the uncertainty in time is not as uncertainty in x or k or omega. We will discuss it a little bit later, but just keep in mind that sigma omega, sigma t star will be half or greater than half. Similarly, if we change our variables to physical variables, then what happens is sigma x, sigma p product is always greater than or equal to h cross by 2, where h cross is the Planck's constant. Similarly, the second relation, by multiplying h cross, we will get sigma e and sigma t star will always be greater than h cross 2. So that means uh, the minimum uncertainty in our measurement due to quantum fluctuation will always be greater than h cross 2. And this is the message of these equations, uncertainty equations, uncertainty relations, and these are called Heisenberg's uncertainty relation in the name of the great scientist Heisenberg. Now let us attempt to understand what this physically means. Momentum and position, these are in classical mechanics, these are conjugate dynamic variables, and in quantum mechanics they cannot be measured with accuracy, indefinite accuracy, simultaneously. So if I try to be more and more accurate and more precise in momentum measurement, then the position measurement goes bad. Similarly, if I try to be more precise in my measurement in position, then momentum precision goes bad. So these two dynamic variables, conjugate variables, they are not compatible with each other so far as measure simultaneous measurement is concerned. These fluctuations, this is arising out of the quantum nature of the fluctuations. You do whatever you like, but when you measure, then due to quantum fluctuations in the system, these variables, momentum and position, which are the conjugate dynamic variables, their simultaneous measurement is not compatible. This is the message. Remember here that this fluctuation is coming out because we represent the reality either by a particle of energy E and momentum P, or by a wave of omega and k, and this representation was achieved by constructing the quantum probability amplitude, taking or superposing the waves in the range of omega varying in the interval omega 0 plus minus delta omega, and k varying in k0 plus minus delta k, and omega is slowly varying with k. So omega k is a slowly varying function of k. So when you superpose these things, you cannot escape the quantum fluctuations during the measurement, and that is the basic reason of the Heisenberg's uncertainty. It is fundamental to quantum mechanics. Similarly, if we want to consider the second relation, that is sigma omega sigma t star is greater than equal to half, or sigma e sigma t star is greater than equal to h cross by 2. Now, number one, uh, the first precaution or the first warning here is that that our fluctuation in time is not quantum fluctuations, number one, and these are ordinary measurement variations due to our technology or the equipments used. They have nothing to do with quantum time fluctuations, because in quantum mechanics time is not taken as a variable, therefore there is no quantum time operator, but it is taken only as a parameter, and it does not show any kind of quantum fluctuation. Of course, there may be some errors in measuring. Therefore, we can say we can talk about the precision with respect to our measuring instrument or measuring technology. That's why, because this fluctuation does not arise from quantum fluctuation, we are writing it as sigma t star and not as sigma t, right? Now, if we what is the explanation of sigma e and sigma t? So let us take a phenomena, or let us take a process in which, when we observe this process or this phenomena, we are observing a particular variable or a particular variable. In this phenomena, we are observing a particular variable b, and we say that the rate of change of b with time, rate of change of this variable b during the process, and this change we are considering the significant change, because see, if there is a certain variable and if it is varying, then we have to take the change from its current value to the new value such that we can differentiate, we can say conclusively that the phenomena has progressed from one phase to the another phase, one stage to the another stage. So that's why we say that if B is changing with time in the during the process or during the phenomena, then d by dt of bracket psi b psi, this is a change, rate of change. And now see that some appreciable or significant change has taken place, and that is delta b. So delta b divided by the rate of average rate of change of this variable d by dt of uh, cat psi b and bra psi can be regarded as uncertainty in t, right? Suppose there is a position uncertainty in the position delta x and change in the position that is called velocity. So if we divide it by velocity, it will be a time, that how much time has been taken in traversing this rate of this change of position with this velocity. This is the idea. So this can be regarded as uncertainty in t, and that means this time interval corresponding to which the variable b has undergone a change of delta b magnitude. This is now delta t, this small delta t has nothing to do with the quantum fluctuations. Whatever quantum fluctuations are occurring, they are occurring in delta b only, right? So the change, the uncertainty in time is indirect, it is not direct. Now during this time, is this is if the change in the energy of the uh, of the wave packet that we see observe is delta E, then we can say delta E and delta T, that is greater than 0, and this is greater than H, and that is what we have taken, that sigma E and sigma T, that is greater than H cross 2. The significant change in the process has taken place during the time interval sigma T star, that is delta T, and in this interval energy uncertainty corresponding to this is delta E. And this, remember, this delta E or sigma E is arising out of quantum fluctuations. So this is a proper uncertainty. So sigma E dot sigma T star is greater than H by 2. This is the another second relation of Heisenberg's uncertainty principle. That's all. Thank you.